Hello everyone, welcome to lecture number 44 in this NPTEL course on Riemannian geometry. So in the previous lecture I introduced this thing called as the index form. So the index form was basically a symmetric bilinear form on the set of all admissible vector fields along gamma. So here gamma is basically just a geodesic. For the sake of notation, gamma goes from A to B to M. It is a geodesic such that gamma of A is P and gamma of B is Q. Then the index form is given by this formula. So there is essentially a term involving the inner product of the covariant derivatives of W1 and W2, and then there is a curvature term. So the importance of the index form stems from the following fact. So suppose gamma is a proper variation, which means that if you take the variation vector field, then that lies that vanishes at the two endpoints, or in other words that lies in the tangent space to omega pq at gamma. Then if you compute the second variation of the energy functional, that is precisely given by the quadratic form associated to the index form. Okay. Alright, and then from this we proved a kind of second derivative test, that suppose gamma is length minimizing, then the index form is non-negative definite. To prove this, we actually used, even though we do not have a formula for the second variation of the length functional, the proof follows from just the Cauchy-Schwarz inequality and the second variation of the energy functional, right. Okay, so today I want to analyze the index form in a little more detail. So let me also from now on, because we are going to keep taking covariant derivatives all the time, we are going to use the following notation. So we are going to, instead of writing dt of w, we are going to write w prime. Instead of writing dt squared of w, we are going to write w double prime, and so on, right. So this will be a convenient notation for us. So recall again the index form which I had written out in the previous slide. So in this new notation, this is just the integral from a to b of w1 prime w2 prime minus the curvature term. So now I want to rewrite this in a slightly sort of different way. So I want to do the following. I want to write the first term in the integrand. So it is this, one can rewrite this as d by dt of w1 prime w2 minus the correction term, which will involve the derivative again hitting w1. So the correction term will involve two derivatives on w1 and the inner product with w2. Okay. So now when you integrate by parts, so the first term, remember, was this. So you rewrite this to be d by dt of w1 prime w2 minus the integral of w1 double prime w2. So for the first term I basically write it as a summation because I want to integrate by parts. Okay. And then the second term I keep as it is. Okay. So by the sort of calculation that at this point we have done quite a few times, one can check, and this is a good exercise for you to write down the details. One can check that when you use the fundamental theorem of calculus, the first term basically reduces to the following: k going from 1 to m minus 1 of del k w1 prime inner product with W2 plus some boundary terms. So yeah, maybe I should write it like this, sorry. So there will be first some boundary terms W1 prime W2 evaluated at A to B, and then minus k going from 1 to m minus 1, the jump in the value of W1 prime inner product with W2 at AK, so the jump in the value of W1 prime inner product with W2 at AK, and then of course the integral term. So when you put it all together, you get an alternate formula for the index. Okay, so this is going to be firstly W1 prime W2 at B minus W1 prime W2 at A, then minus these terms coming from the fact that W1 is merely continuous, but it need not be differentiable, need not be smooth, for instance. So you might have a jump in the values of W1 at these non-smooth points, okay, and then minus you have an integral term. So in fact the integral term can be written as W1 prime plus the curvature applied, the curvature endomorphism inner product with W2, okay. So that is an alternate formula for the index form. So one thing to note is that if W2 belongs to the tangent space to omega PQ, which means that W2 of A is 0 and W2 of B is 0, then the index form takes a slightly simpler form. It will just be the boundary terms will go away, so you would just have this. Okay. Alright, so this if you look at this sort of principal integral term, that motivates the next definition. So here is a definition which will be very useful in analyzing minimal geodesics. So for the rest of the course this will be a sort of one of the most important definitions. So let gamma be a geodesic a smooth vector field so this is now a smooth vector field along gamma is called a Jacobi field if this sort of principal integral term in the alternate formula for the index form vanishes completely. So if j double prime plus r of j gamma dot is identically 0 on the interval a to b, okay. So this thing is called Jacobi equation. So a Jacobi field is one that satisfies the Jacobi equation, okay, and then our notation will be j of gamma. This is basically the set of all Jacobi fields along gamma. Okay, so one sort of observation is the following. So if then for all w in the tangent space to omega pq at gamma, so you take all w's which vanish at the two endpoints, the index form is actually 0. Okay, why? Because you just go back to the formula, because w vanishes at the endpoints, we can use this formula for the index form. But now by definition a Jacobi field is smooth, so these jump terms will all be 0, and then again by definition, because the Jacobi field satisfies the Jacobi equation, the integral term would also be 0, right. Okay, so the goal is actually is to prove the converse of this. Okay, so that is going to be the main goal for this lecture. In that, if you have a Jacobi an admissible field which so that I of j comma w vanishes for all w in the tangent space, then that means that J has to be a smooth Jacobi field. So I'll get to that in a minute. Before we prove a converse, we need the following basic proposition on the existence and uniqueness of Jacobi fields. Okay, so let gamma be a geodesic then given any vectors v and w, the tangent space at gamma of a to m, there exists a unique Jacobi field such that these are the initial conditions. So J of a is equal to v and J prime of a is equal to w. So in particular, this implies that the space of all Jacobi fields is a vector space of dimension 2n. Why 2n? Because the choices of v can be any tangent vector at m and w can be any tangent vector at n, tangent vector to m at gamma of a. For each of these you have basically an n dimension worth of choices, right, because the tangent space at that point is n dimensional, and once you specify v and w, your Jacobi field is uniquely determined. Okay, and why is it a vector space in the first place? That is because the Jacobi equation, so note that the Jacobi equation is a linear homogeneous, because the right hand side is 0, second order ODE. Okay. So in other words, in local coordinates, right, you would have the Jacobi equation would be something like this. So suppose J of t is right? This plus you are taking the covariant derivative, so there will be some sort of covariant derivative parts. So maybe let me just write this as a covariant derivative plus some sort of curvature terms, which will be of the form right. So this is clearly in terms of these components, one can write this down. I do not want to sort of write it down completely, but this is a good exercise. One can check that what you get is actually a linear second order ODE. Okay, it is a good exercise to sort of take these coordinates and check that this is so. So then to prove the proposition, I will leave it as an exercise. You basically use the existence uniqueness theorem for such ODEs. So the idea is that you have this curve gamma from, let us say, P to Q, you are at some point here, you can draw a coordinate neighborhood so that you can identify this as an open subset inside Rn, and then for the components of the Jacobi field you can write it as a sort of linear second order ordinary differential equation, and hence obtain a global solution on this interval. Okay. Then let us say you have another coordinate neighborhood that intersects this, you choose another initial condition here given by your solution on the first interval, and then by again the ODE existence theorem you will get a solution on this time interval, and so on. You keep going all the way up to Q. So this is something similar to how we had shown that parallel transport exists on the entire interval A to B, right. It is the same argument, except now you have a second order ODE, but it is still a linear ODE, so the same theory applies. So I will not elaborate on this point much more, but I would encourage you to really write down a proof of this proposition for yourself. Okay. Maybe let me make a remark that the corresponding boundary value problem so that means I specify j of A to be some vector v and j of B to be some vector let us say v1. This is now at the tangent space at gamma of B. This may not have a solution. Okay. And in fact this not having a solution is related to an important concept called as conjugate points. So so the initial value problem always has a solution, but the boundary value problem may not have a solution. Okay, so the key proposition that I want to sort of prove is the following, that J is a Jacobi field if and only if, so this is the converse that I was alluding to before, if and only if for all vector fields, admissible vector fields along gamma that vanish at the two endpoints, we have that the index of j comma w is 0. Okay. This is equivalent to J being a Jacobi field. Okay. All right. So so as we saw that suppose J is a Jacobi field, then this is actually trivial, right. This we saw in an earlier remark. Let us prove the converse. Okay, so suppose J is sorry, so maybe I should modify the right. So the statement is that J is a Jacobi field if and only if J is an admissible vector field which has this property that for all W in the tangent space to omega PQ at gamma the index form vanishes, right. So let us take some admissible vector field such that the index form vanishes for all W in the tangent space. Okay. So the first claim is that so for notation let as usual let us take a partition such that J restricted to these closed intervals is smooth. Okay, so the first claim is that J satisfies the Jacobi equation on these open intervals. So wherever J is smooth, J satisfies the Jacobi equation. So the proof of this is similar if you remember the proof that a critical point of the first variation formula is they are all I mean the proof that the critical points of the energy functional are all smooth geodesics. Remember the proof followed two main steps that the first step was to show that that your gamma is a broken geodesic, it satisfies the geodesic equation wherever it is smooth, and then to show that it is in fact smooth. So we are going to do the same thing for these Jacobi fields. So let us first prove that they are actually Jacobi fields on wherever they are smooth and then prove that they are also globally smooth. So how do you prove this? So let we again use the same bump function trick. So let chi be a smooth function such that I want chi to vanish at each of these problem points and at the other points I want chi to be strictly positive. Okay. So in other words I want chi to be a function that looks like this. So this is A, this is B, you have your partition points here. So it is a function that basically looks like this, okay, and it is smooth, so on. So let W of t be equal to chi of t times J double prime plus R of J gamma dot. Okay. This is clearly going to be an admissible vector field, and because chi vanishes at the two endpoints this is going to be in the tangent space. So now let us compute the index of this. Okay, the index form applied to J comma W. So by hypothesis this is 0 because W belongs to the tangent space. On the other hand, what is this? By our formula for the index form, this is going to be this. Okay, minus this okay, but W at AK is 0 for all AK and W is given by this formula. So this is just going to be minus the integral from A to B of chi of t norm squared of this vector field. Okay. but because chi of t is strictly positive, this is going to be strictly negative unless this vector field is identically 0. Whenever chi t is strictly positive, but chi t is strictly positive precisely at the points where j is smooth. So that means that j satisfies Jacobi equation for all t not equal to ak. Okay, so that proves the first claim. The second claim is that j is in fact smooth. Okay. What is the proof of that? So it's actually enough to show that the jump in the derivative of the Jacobi field is 0. Why? Since then one can define so the derivative at these problem points will then be well defined. Okay, but then if the derivative is well defined, we just look at, for instance, this ak minus 1, ak plus 1. So the Jacobi field is well defined and smooth here, it's smooth here, right. On the other hand, the Jacobi field on the so let us say we put j minus as the Jacobi field on the right side of the interval, and j plus sorry on the left, and the j plus as the Jacobi field restricted to the left, to the right. Okay. Then we have that at ak, of course the values agree because j is a continuous vector field, but by if we show that the jump in the derivative is 0, then the derivatives will also agree at these points. Okay. But then by the uniqueness of by this proposition on existence and uniqueness of Jacobi fields, the solution to the Jacobi field will now exist on the entire interval, right. So j there exists a j tilde on the entire interval such that j tilde restricted to this is j minus, and j tilde restricted to ak plus 1 is j plus. Okay, so in other words this implies that j tilde restricted to the interval ak minus 1 to ak plus 1 was your original Jacobi field itself. Okay, but this guy is smooth by the existence uniqueness theorem for second order linear ODEs. So that would imply that your original Jacobi field is also smooth. Okay, so it's basically enough to prove that these jumps all vanish. And how do you do that? You again use the bump function. So now the goal is to show that that these things all vanish for all k. How does one do that? So let so again by using a bump function, let x be an admissible vector field such that at these sort of bump function at these problem points this is precisely this. Okay. So this can be constructed using the bump functions. So again, this is something that you should write down a proof for yourself. I am leaving all these sort of open ended precisely because I want you to actually go and try to write out a proof for yourself. These are good exercises and this is a good way to learn. So then and one can also make sure that at the boundary this actually vanishes, okay. So that means x actually belongs to the tangent space. So then again, if you apply the index form on j comma x, that is going to be 0, but this is going to be minus summation k going from 1 to m minus 1 plus this principal integral term, right. But this thing is 0 by our first claim because J satisfies the Jacobi equation on wherever it is smooth, and by our choice of capital X, all these terms are precisely this squared, which is strictly negative unless the jump is 0 for all k, right. So that proves that accomplishes what we set out to achieve. Okay, so that's the proof of this proposition. In the next few lectures I am going to really study these Jacobi fields in a deep way, and we are going to use Jacobi fields to probe when a particular geodesic is minimizing or not, okay. So that is going to be the sort of main aim for essentially I think what will take us through to almost the last week of this course, right. Alright, so that is it for now. I'll thanks for your attention and I'll continue next time. Thanks.